Well, hello everyone. Luckily, there are only 3 of us presenting today, so you're going to not feel too overwhelmed by the time I'm finished here, but I have a lot to get through, so bear with me. I was lucky enough to secure an interagency agreement between DNR and Evergreen, which allowed me to do this large project as part of my work at DNR, so I just want to start off by thanking them. There are many factors that will negatively impact eelgrass, with light and temperature more so than any other. Similar projects have been done before, but on a much smaller scale. So with my project, I wanted to test how different populations of eelgrass would perform in the upper threshold of elevated water temperatures. Okay, my wheel is spinning. I'm sorry, guys. Zostera marina is the largest of 2 native vascular seagrasses, also known as eelgrass, and they are ecosystem engineers and therefore play a vital role in maintaining nearshore ecosystem functions. As I've mentioned, they are ecosystem engineers, which means that they create and modify habitat that significantly affect several other species. You can see from this image that in the Pacific Northwest, it is connected to 394 species that we know of. It provides shelter and protection, serves as a food source, and it also is a spawning and nursing ground for fish. Additionally, eelgrass contribute to primary production, soil formation, and nutrient cycling. It has been estimated that the global value of eelgrass is worth $81,000 per hectare per year. And globally, eelgrass is in decline. Locally, eelgrass will be pushed polewards as water temperatures increase due to climate change. So through this project, I wanted to see how eelgrass would perform in the higher threshold limit and how this would affect factors like growth, reproduction, and mortality. By doing this, we are also able to identify which of the populations are more resilient to thermal stress so that this population can be considered for restoration purposes. But by selecting the most resilient population for restoration, we can help to ensure the survival of the species in Puget Sound. The 5 areas that I chose covers the main oceanic regions of the Puget Sound and is also part of DNR's well-established ocean acidification network. And the 5 sites that I chose were Cherry Point, Elliott Bay, Fidalgo Bay, Nisqually Reach, and Willapa Bay. These sites also included areas with the highest and lowest mean temperatures, with Fidalgo being the lowest at 7.4 and Willapa Bay being the highest at 12.48. This experiment took place over 6 weeks during summer and consisted of 12 tanks with 4 treatment levels, 14, 17, 20, and 23. And there were 3 replicates of each treatment level. Also, thank you, John, for pointing out that I had to construct and design the system that you see here. So there was a lot of, that equated to a lot of man hours and some head slamming, but we got it done. This was a flow-through system with water being pumped from the Puget Sound and then filtered and chilled before it's pumped into these tanks. Apex controller, which are those orange things you see there, they were used to monitor and record water parameters, and the lights of these tanks were set to a 12-hour photo period. So we collected the eelgrass from the 5 locations and we placed them in coolers to transport them to site. Once we had them on site, we cleaned them and separated the eelgrass with at least 5 internodes. And after we sorted them out, we picked 5 random shoots from the bunch and standardized them to 4 internodes each. They were then attached to this cage with zip ties and labeled accordingly. The morphology and the survivorship. So each week, 3 random shoots from each population in each tank were measured, and we recorded the shoot count, the shoot length, the sheath length, the sheath width, and the total number of leaves. For the growth rate, we used the pinprick system, and we basically just prick it right below the sheath, and you wait a week, and when you come back, you can see as the grass is grown, you could follow the pinpricks. And so to measure the growth, you would just measure the distance between the 2 pricks. Samples were tested for photosynthetic efficiency by evaluating the chlorophyll fluorescence of the leaf shoot adjacent to the meristem, that is the youngest leaf, using a PAM. Plants were tested 1 hour before the photo period started, while it was dark and adapted, and cellular respiration occurred. The PAM reading gave me an FV over FM reading, and that is what I used for the statistical analysis. Initially, when this is just to show you the different sizes of each population, also just randomly picked. And with our initial measurements, we found that Fidalgo had the longest shoot length at 114.9, and Elliott Bay the shortest at 48.1. And when it came to the photosynthetic yield using the PAM, the Elliott Bay had the highest at 0.84, and Fidalgo Bay had the lowest at 0.78. Okay, now to all the confusing good stuff. Mean summaries were calculated for all treatment levels, and I decided to pick 4 performance measurements, and there is more data for somebody else to take on as a thesis, but I was definitely not going to use all the data that I gathered for this project. I normalized the data for shoot length to give me a starting value, as this is an absolute measurement. This allowed me to determine a loss percentage from the initial measurement or count for each week. For shoot length, all of the populations decreased in treatment level over the course of the experiment. There was substantial blade loss up to the sheath amongst all populations by week 2 in 23-degree treatment. Fidalgo Bay had the least percentage loss for treatment level 14 degrees Celsius, and overall the slowest blade loss at 17 and 20 degrees. For the blade count, I also normalized the data to give me a starting value, as this is an absolute measurement. For Fidalgo Bay had the lowest percentage loss for treatment at 14 degrees, and and overall the slowest blade loss at 17 and 20 degrees. I did not need to normalize the data for growth, as there is a change in value over time. Now Fidalgo Bay had the most growth for treatment level 14 degrees, whereas Willapa Bay had the most stable growth. And finally, moving into photosynthetic yield, I didn't need to normalize this either, as the reading FV over FM is a ratio value. And here we can see that Fidalgo Bay had the highest photosynthetic yield in treatment level 14. Okay, now this might look very confusing, and it is, because I had to run over 50, I think it was, t-tests. These are one-tailed t-tests with to see if there was a significant difference between all the possible pairs of the 5 different populations. The p-values for shoot length from a one-tailed t-test with significance determined with a cutoff of smaller than 0.05. All significant p-values under that threshold are highlighted in orange here. First one, the shoot length, there was a significant difference between Elliott Bay and Cherry Point in treatment level 14, 20, and 17. Cherry Point and Nisqually Reach was significantly different than every other population at 17, and there was no significant difference between the populations at 23. For blade count, There was a significant difference between Elliott Bay and Cherry Point in treatment level 14 and 17, whereas Fidalgo Bay was significantly different than every other population at 17. And again, there was no significant difference between the populations at 23 degrees. The growth, Fidalgo Bay was significantly different than every other population at 17. And again, no significant difference between the populations at 23. The photosynthetic yield, Cherry Point and Nisqually Reach was significantly different than every other population in treatment level 17. And Cherry Point was significantly different than 3 other populations in 20. And again, there was no significant difference between the populations at 23 degrees. This single factor temperature experiment considered 4 water temperatures spanning the natural upper threshold range of Zostera marina. The goal was to identify the most resilient population, and previous work has shown that optimal temperature range lies between 15 and 20 degrees, and that temperature above that temperature is considered lethal. In our mesocosms, we exposed five different eelgrass populations to 4 treatment levels, and in general, the highest temperature level, 23 degrees, was lethal to all populations when compared to the lowest treatment level of 14 degrees. The key findings of this study were that Fidalgo Bay populations were more tolerant to thermal stress than all other populations. Overall, Fidalgo Bay had the lowest percentage loss of shoot length, slowest blade loss, most growth, and highest photosynthetic yield. The initial morphological measurement indicate that morphology is connected to eelgrass performance, as Fidalgo Bay had the longest blade length, sheet width, and sheet length. Fidalgo Bay also outperformed all populations, even though it had the smallest FV over FM and the coolest daily mean water temperature. This study also showed that higher temperatures will significantly affect growth and survival in treatment levels 17 degrees and higher for all populations. Changes in eelgrass performance occurred noticeably during week 2 in all 4 performance measurements. This indicates that long duration thermal stress has negative consequences for eelgrass production and resilience. We're almost there. Okay, eelgrass communities will face considerable stress over the next several decades. As shown by other studies, elevated water temperatures is one of the most important negative effects from climate change. When comparing the 4 treatment levels, the higher treatment temperatures had noticeable higher mortality, which indicates that a change to a higher climate regime will cause higher mortality. Certain populations are better adapted to handle higher temperatures, and by identifying which populations are more resilient to these increasing water temperatures, can assist resource managers develop effective mitigation and restoration strategies. One such way would be to use the most resilient population as a donor for future restoration purposes. This also prevents disruption of less resilient population sites that are more vulnerable and sensitive. There are ethical questions that are raised from using genetically different populations, as this could have irreparable effects that we might not be able to think of now. The dilemma might be overlooked due to the urgency of the problem and survival of the species. Implication of loss of species has ramifications for the organisms that depend on it. Further studies are required to identify other similar or more resilient populations, and it is therefore suggested that the same study is done with populations that were not included, for instance, the other 5 sites from the anemone network, or populations from the Strait of Georgia and the Canadian coast. Further studies should also include light availability, perhaps, or pH, and maybe a combination of 2 factors like light and temperature. The study limitations of this project were that not all natural conditions could be simulated in this artificial environment, and the eelgrass was already placed under immense stress once removed from the sediment to keep the rhizomes exposed during the experiment. That was also detrimental. So with that, it concludes my presentation, and I'm sorry I did go over 15 minutes.